Thus, the first two experiments allowed us to appreciate that TCP establishes a connection before file transfer, and even if there are packet losses, TCP can ensure reliable data communication using sequence numbers and acknowledgement numbers. The third experiment is aimed at understanding the rate at which the TCP connection faces traffic in the network. This is essentially controlled by what is called as a congestion window, which is the amount of unacknowledged traffic sent by the client which is in the network. This is done rather than sending one packet at a time and getting an acknowledgement, which will be like stop and wait. TCP allows many unacknowledged packets to be over the air so that it can utilize the available network resources efficiently and improve the throughput. The focus of this particular experiment is going to be how the congestion control algorithm probes for bandwidth in the network, how it senses the congestion, and how it avoids the congestion. Finally, we will also look at how the congestion control algorithm essentially makes the throughput of the network. We will consider again as the same network as in experiment 2 on reliable communication with a small modification. Instead of transferring 10 packets, we will consider a very large file transfer so that we can appreciate the congestion window evolution over a long time and also appreciate the long-term average throughput with the congestion control algorithm. A quick overview without any details. TCP continuously searches for available bandwidth, so it continuously increases packets at any time. Upon seeing congestion, which is perceived either by packet loss or timeout, it reduces the amount of unacknowledged packets and adapts certain parameters so that it does not repeat the same mistake that it did. So the congestion window evolution continues to change, the parameters continues to change till it attains a steady state depending on the network congestion. In this experiment, we will review 3 different versions of TCP, the primary versions, old Tahoe, new Reno, so that we appreciate the slow start phase, the congestion avoidance phase, fast retransmit, and fast recovery. As mentioned before, we'll consider a large file transfer to understand long-term effects. I'll leave the floor again to Krishna to simulate the experiment.
Thank you, sir. Let me go back to the previous network setup. In the same network setup, we will enable the basic congestion control algorithm, old Tahoe, and we also give a large file size. And we change to be slightly less. Now we run the same experiment for 20 seconds. So since we gave a large file that is being fragmented into multiple segments, Once the packets are fragmented, the simulation will start. The file is being transferred. From the Wireshark, we select any particular data segment and we go to TCP stream graphs and the window scaling, and then we switch the direction. Now we can see the congestion plot. Now we can see the congestion plot. For the congestion control algorithm we selected, that is Old Tahoe. Now I hand it over to Professor.
Thank you, Krishna. This is roughly what we saw from the simulator, the congestion window evolution over time. Here I have plotted the same information from the packet trace. So we will later upload a link on how to get the congestion window evolution from the debug mode. Sorry, it's not the packet trace, but from the debug mode, where we have more clear and accurate evolution of the congestion window over time. I'm highlighting some region to identify the important phases. Two important phases of the Old Tahoe, or slow start phase and the congestion avoidance phase. In the slow start phase, the TCP is aggressive in increasing the congestion window, and in the congestion avoidance phase, it is less aggressive. Let me identify what happened in this highlighted space. The orange roughly indicates a time when a packet was lost, and red indicates a time when there was a timeout. Old Tahoe reacts to packet loss only with timeout and not with duplicate acknowledgements. So when a timeout occurred, then the following occurs. The slow start threshold, which is set to the current congestion window by 2. So from here, 64 kilobytes, it's reduced to close to 32 kilobytes. Then the congestion window is reset from 64 kilobytes to the initial value, whatever is one MSS, or the initial value, whatever is standard, and then you enter the slow start. From the congestion window of 1 MSS, or the initial value, all the way up to the slow start threshold is called as the slow start phase. And from the slow start threshold all the way to the next packet loss or the congestion window max is called as the congestion avoidance phase. What happens in the slow start? In the slow start, for every acknowledgement, the congestion window is increased by 1 MSS. That is it. So it is very aggressive. For every packet acknowledged, the congestion window increases by 1 MSS. In the congestion avoidance phase, it is less aggressive. For example, if there are 10 packets, unacknowledged packets, or if CW is 10 MSS, then the congestion window is increased only by 1 MSS for 10 acknowledgements. So it is less aggressive in the congestion avoidance phase. This is to ensure that the TCP protocol does not repeat packet losses or does not see packet losses again and again. This Old Tahoe, because it reacts to packet losses only with timeout, can lead to very poor performances, especially in large BDP scenarios, large bandwidth relay product scenarios. So a correction was brought in Tahoe, where upon reception of multiple duplicate acts, the TCP is allowed to infer packet loss and it can respond. Moreover, the reception of multiple duplicate acts kind of indicates that the packet losses are limited or random, so it can respond without any fear of a lot of congestion in the network. So the response is very similar to old Tahoe. Upon receiving triple duplicate acts, the Tahoe does the following: it sets the threshold window by 2. It sets the congestion window to 1 MSS or whatever is the initial value, and then it enters the slow start phase till the congestion window reaches the slow start threshold, and then it enters the congestion avoidance phase till the next packet loss or till it reaches the max congestion window. So the key difference between old Tahoe and Tahoe is it reacts to packet loss with triple duplicate acts, and then it retransmits the packet, which is essentially the idea called fast retransmit. Unlike old Tahoe, there was one more revision to this idea, which is called fast recovery. Remember, once you receive triple duplicate acts, even Reno would reset the congestion window to 1 and would quickly scale to slow start threshold of congestion window by 2. The new Reno essentially eliminated that resetting the congestion window to 1 and essentially eliminated the entire slow start phase. And this is roughly what it does. Receiving triple duplicate acts, it would enter what is called as fast recovery, and upon receiving the correct acknowledgement, rather than going to CW equal to 1 MSS, it will start with half of the previous CW and then enter congestion avoidance phase directly. This ensures that the congestion window does not fluctuate a lot and the bandwidth is regularly probed while not creating too many congestions. Here we are summarizing the key ideas of new Reno, which is an evolutionary algorithm from old Tahoe and Tahoe itself. To begin with, you are in the slow start phase with congestion window 1 MSS and some slow start threshold. For every new acknowledgement, you increase the congestion window by 1 MSS. If the congestion window is larger than the threshold, then you enter congestion avoidance phase, where for every new acknowledgement, you are less aggressive in increasing the congestion window. Upon a packet loss and triple duplicate act, you enter fast recovery, and upon a correct act, you enter congestion avoidance. In the event of timeout, you always enter the slow start phase, where the slow start threshold is set to congestion window by 2 and the congestion window is initialized to 1. The congestion window algorithm not only controls the amount of unacknowledged packets, it also controls the throughput achieved by the different algorithms. Here we plot the long-term average throughput of old Tahoe and new Reno, and as expected, new Reno has a better, it appreciates better. The congestion control algorithm also determines the long-term throughput, which can be predicted using simple analytical formulas. Here we highlight that for the lossless link, the congestion window algorithm, the congestion window at any time allows you to predict the throughput as the congestion window divided by the RTT, the number of unacknowledged packets divided by the total round trip time that it takes. For the lossy cases, one can actually predict the performance using standard renewal reward theorems, and there are a good number of references including Koros and Ross, which allows you to compute the throughput. In general, such analysis can be extended to a variety of TCP versions. The conclusion is TCP does end-to-end congestion control and not it doesn't need any support from the local network. It responds to delays and duplicate acknowledgements, and the congestion control algorithm essentially affects the long average. Recent and popular versions like cubic, compound, and HTCP have different algorithms for managing the congestion and are suited to a variety of new network scenarios of interest. The last exercise here is on how network resources are shared with multiple TCP flows. For this experiment, we will consider 10 clients trying to transfer a long file, a very large file, using TCP. The network setup is very similar. The link speeds, all the link speeds are 10 Mbps. The propagation delay is 25 millisecond per link with an RTT of 100 millisecond, and the file size is a large file as was inferred. Here I am plotting the long-term average throughput of the 10 clients. And if you notice, each client approximately gets 1 Mbps, which is a fair share of bandwidth for each client of the 10 Mbps link. We can then conclude that TCP provides a fair access of resources to all the competing clients. Here we plot the share of the throughput over short intervals. Over every 100 millisecond, what is the throughput received by the different clients? You can clearly see that on an average, the sessions have a share of 1 Mbps. However, the throughput fluctuates a lot. This is because of the way the TCP evolves and the fact that the BDP is such that there are buffer overflows continuously in the network. While TCP provides a long-term fair throughput access, in short term, there is continuous fluctuation in the throughput, which might affect many applications. A conclusion is network resources are shared equally in long term. However, in short term, sharing is not fair. Performance critically depends on link capacity, buffer, algorithm, the congestion in the network, etc. And if we are seeking to improve fairness, one can consider queue management strategies. I would like to conclude that TCP is a very important protocol that has been the backbone of our internet. It provides end-to-end congestion control, end-to-end communication service. Key functionalities of TCP, unlike UDP, are reliability, congestion control, and multiplexing. The success of TCP is its ability to dynamically adapt to any network and give a reliable and a good service. I strongly recommend you to look at recent versions and the logic behind algorithms such as cubic, compound, and HTCP. Few remarks on recent advances in transport layer protocols. Kindly look at Quick UDP internet connection, which is used in Chrome, the browser. In Quick, the application layer is geared to provide a reliable, orderly connection, is geared to provide congestion control using UDP. Kindly, I would recommend it as an exercise on the advantages of using TCP versus UDP in the context of Quick. Recently, there has been attempts to develop ML-based, machine learning-based congestion control algorithms. Again, I believe that this is another recent trend which might be of great interest in the future. Some suggested exercise. Performance of TCP as a function of the bandwidth delay product. Performance of TCP as a function of buffer size. Interaction of TCP versus UDP. Performance of TCP over wireless. And impact of algorithms such as random early drops, weighted fair queuing on the performance of TCP. These are very basic experiments, and any student or practitioner who wants to appreciate TCP should appreciate the effect of these parameters as well. I'll conclude the presentation with the basic and key references for TCP or RFC 5681, articles, classic articles by Cerf and Kahn and Jacobson, and some very good references in Computer Networking, Cross and Ross, and TCP IP Illustrated, volumes 1, 2, and 3 by Stevens. I thank everyone, Pranav Krishna, for the opportunity, and thank the audience as well. Thank you.
Thank you, Professor. And since we are running short on time, I don't think we'll be taking any questions today. In the event you have questions or you wish to communicate with us, you can always just send us a mail at sales@tetcos.com or to support@tetcos.com, and we are happy to respond immediately. Thank you all again for attending this webinar.